Alright, so on the first day of our CCNP course, we introduced a simple review of routing. We discussed what routing is for, so what does our router do? Then we thought about how our router forwards data traffic. We used a very simple sentence to summarize. So, the router forwards based on the routing table, based on the destination IP address, find my router, our built-in, our internal routing table. Find the corresponding route to the destination IP address. So, our corresponding route. Then throw the data packet out from our exit interface. We also mentioned, by default, our router will only have direct routes. When our interface is up, our link is also up. Then this link can be accessed normally. Then our interface is configured with an IPv4 address. Then the router can have this direct route, our router interface on the other end. As long as it's an IP address on the same link and subnet, our routing system access is the benefit brought to us by direct routing. Then we talked about a fully interconnected. In our work, we aim to enable our data volume to be forwarded across multiple sites. Basically, we achieve what's called full interconnectivity, our router. Our network's devices must have routing entries for all other sites. At that time, we thought, since our router by default only has direct routes, we can only access the direct links of our own router. So the router's non-direct links. How do we forward without segment routing entries? We thought of manually inserting our static route, manually inserting static routes. We talked about non-direct routes. We can divide into static routes and dynamic routes. Then static routes are manually inserted by us. We can manually specify to which network segment to which subnet. We should route this data packet through which interface. Or we can specify. You direct traffic to a certain network segment or subnet. Then you throw the packet to which next hop address. This is our way of writing static routes, but we also discussed if you are in a large network deploying static routes, could that cause a lot of problems? Therefore, today we first need to mention the advantages and disadvantages of static routing. The advantage of static routing is quite obvious. It is indeed very apparent. The advantage of static routing is its simplicity, called simplicity, efficiency, and stability. The advantage of static routing is very straightforward. It is simple, efficient, and stable. For example, to make a router, if I want router R1 to have a route entry for a non-directly connected network with a route for the 192.168.23.0/24 network, I only need to use one command line on R1's router. Apply a command line IP route 192.168.23.0, then specify the next hop address. Okay, then, our router immediately has a route entry to the network. That's static routing. One command line can solve our router for access to a certain network very quickly efficient, right? It's done in one go stable, so static routing actually has its basis for existence. Whether it can exist in our routing table. Actually, its judgment standard is simple, called next hop reachability. So we tell R1, now you go to 192.168.23.0. Your next hop address should be 172.16.12.2. As long as this next hop address is reachable, able to be accessed, then this static route can be stably exist in our routing table. Only if the next hop is unreachable will this static route become ineffective. Or later, we will discuss administrative distance and the use of metric values. Students, next, we will talk about how static routing is simple, efficient, and stable, which makes it very practical in a small network. Why a small network? Because it's suitable for small networks. Why, students? For instance, if our network only has, say, 3 routers and just 2 network segments. Then for R1, I just need to configure one route entry for a non-directly connected network. Then for R2, we already have direct routes. R3, we configure a route entry for a non-directly connected network. Okay, the whole network is interconnected. Everyone can access it. But if there are 15 devices, like say 15 devices interconnected pairwise, there are only 14 network segments in total. So, to enable them to access each other, if you want them all to be able to access each other, each router would only need to enter about 12 to 13 static routes. But think about it, students. In a large network, let's say we take a lab diagram, our CCIE lab exam, the current topology diagram, I'll show it to you here. Here, for instance, this diagram, I'll try if I can draw it here. Maybe extract this diagram. Then here we look at this PDF. In such a diagram, if we were to use static routing to achieve full network interconnectivity, here's the problem. Full interconnectivity is simple, but every device must have route entries for all network segments. How many network segments are there here? Like R1, R21, I have direct routes, 4 direct routes already. Okay, then all the other non-directly connected network segments. If I want R1 to be able to access them, I have to write static routes. 1 static route 2, 3, 4, 5, and then there's a bunch more. Here, so if you want a router in a large network to have route entries for the entire network, imagine how many static routes you'd need to write for R21. We'd need to write route entries for all networks. R22 also needs to write. If you want to achieve full network interconnectivity, every device must have routes for all networks. How many routes would R21 need to write? How many would R22 write for a person, a human? You have to write so many static routes. It's exhausting in a large network using static logic to configure. You definitely as a person. First, it's tiring, this repetitive work. Furthermore, students, this routing is very important. It affects whether your network can communicate you as a person. Everyone has physical strength. If you work too long, configuring such a large network, your brain will definitely become fatigued. So it's easy to, after all, it's manual. It's labor-intensive manual configuration. We manually configure static routes in the network, which can easily lead to suboptimal paths or loops. First, let's discuss what a suboptimal path is. For example, let's take a network, just grab our CCIE topology map. After all, students may need to take tests on this. They might be tested on this, like a topology diagram. So, if I now want R21 to have this network route entry holding a October 2nd, 21, 0/30th network route. If I use static routing, then there are 2 next hops to choose from via 201 or 202. In our human perspective, from a third-party view, we think actually R21 accessing via 202 is our best choice of path. It directly reaches there. But if we, as humans, have configured 100 static routes already, I'm tired. Then I might... What? I might accidentally give it to 22. If it's 22, I might accidentally configure it wrong, leading to, what does 200 do? It then goes to 202, and then it goes further. So what might we need to do? We've taken a long way around. Did we circle around? We didn't take the shortest path to forward this data packet? Isn't this a waste of our device resources? Right, students. Secondly, so if you as a person need to configure such a static route in the network, it's very likely to have a configuration error. Your mind is not clear. You've configured a lot of practice. I've made a lot of configurations. Then you might what? Next hop points to R2, R22 points to R201, 201. Accidentally, we pointed to the wrong next hop address. Point where? Point to 21. So students, right? For R21. Going to the 2.21 network segment. How to forward? Data packet given to 22. How does 22 forward? Route entry. Next hop, given to 201. 260 given to whom? Given to 21. Then 21 looks at the destination address of the 21 network segment. Again, given to whom? Given to R22. As a person, it's possible I say it's possible. You do to configuring a lot of static routes. After all, with static routes, you decide your own next hop address, out interface, or you decide yourself. You are bound to possibly make a mistake. Suppose you configured a loop that would be severely impactful. Students. So for a network, if you use static routing for configuration, simple, efficient, stable is its greatest advantage, including many of our production networks. Because we aim for stability and efficiency, stable and efficient. So in our production network, it's quite large. We also prefer to use static routing for deployment to make it stable. But what is the precondition? As a person, you need to try to eliminate loops. But if the network is too large, you use static routing too. Don't just use the lab's diagram. you're killing yourself. So say in a large network, a medium to large network, the drawback in medium to large networks is the high volume of configurations, not quality but quantity, a high volume of configurations. Then there's another problem for our static routing. It can't rely on itself to achieve what's called topology. It can't adapt to changes in the network's topology. What does that mean, students? Suppose in a network, R1, R2, R3, we've already deployed the network R1. We've written a route to the 23.0 network. Then for R2, we have two direct routes. For R3, we've also written a route to the 172.16.12.0/24 network. At this moment, the whole network is interconnected. But if at this moment we added a new network segment behind R1, we've added another network segment. It's, for example, 192.168, 3.0/24. So to ensure the whole network can communicate, all our routers must have the capability to access this network segment. Okay, then our R2 needs to write a static route pointing to 3.0 next hop address. R1, R3 also needs to specify a next hop address based on the destination network segment. Write a next hop address pointing to 0.1. Think about it. If a new network segment is added in the network, we need to write a static route on all routers, except the one with the direct route. They all need to write a static route that can access this network segment. So if in the network a certain network segment's address is removed, then to avoid these what we call garbage configurations existing on our devices, we still have to undergo what is called certification. This certification level 2, certification 3.0. You need to delete those garbage configurations. So if you use static routing, it can't automatically adapt to changes or removal of a certain network segment in the network. This is also a problem with static routing. So we think, can we let this device itself calculate, choose its own route entry's next hop address, adapt itself based on changes in the network's topology? So we think of using dynamic routing. Our non-direct routes are divided into static and dynamic routing. Dynamic routing actually characterizes dynamic routing protocols. Dynamic routing protocols have many types. Sorry, my pneumonia has not completely healed. Hello, just leave it at the door. Thank you. Yes, just leave it there. Thank you. Goodbye. So we are. Why is WeChat so noisy today? Let's pause WeChat for a while, I won't be disturbed. So we definitely need to try to reduce our manual workload and aim to create a superior routing decision, because manual routing can lead to suboptimal paths and loops. So we think about dynamic routing protocols. Now, dynamic routing protocols. Students, what are they primarily? They're categorized and classified. Dynamic routing protocols have many types. Each dynamic routing protocol works differently. They contain different technical points within them. What we mainly need to understand is their classification. Secondly, how each dynamic routing protocol works. Firstly, the classification of dynamic routing protocols. The simplest classification is based on the essence of our routing protocols, or rather, their algorithms for classification. Classifying based on essence and algorithms, it is mainly divided into two types, mainly into two kinds. The first kind is called distance vector dynamic routing protocol. The second kind is called link state dynamic routing protocol. Then, running dynamic routing protocols. What are the advantages? Firstly, the most straightforward automatic calculation of route entries. Calculating the next hop address. Automatically calculating route entries and next hop addresses. Submit to the routing table. We don't have to consider as humans this route, this data, this network segment, next hop, who, how to go, right? Now the dynamic routing protocol can calculate on its own. I can determine based on the topology in the network or its route entry transmission direction. I know how this data packet should be forwarded. Secondly, it can automatically adapt to changes in the network topology. So if we add a network segment in the network, we only need to run the dynamic routing protocol on that one router. Then the other routers can automatically generate a corresponding route for that network. That's one thing. Secondly, if a network segment is no longer in use, we just need to remove that network segment like this map. I don't need anymore. then other routers' routing tables can also automatically remove this network. The route entry for this network segment, I can automatically adapt to changes in the network. And when I find, for example, that the current path has a problem, like when we navigate using a navigation app and find congestion ahead, it can automatically switch us to another path. Like if there's a river ahead, right? We automatically take another road. That's the second point. The third point, then our dynamic routing protocol mainly what? It is suitable for medium to large networks where configuration volume isn't it quite suitable? It's suited for medium to large networks like in our CCIE lab exams. Here we use OSPF dynamic routing protocol, and the configuration volume is very, very low. These two areas are covered by OSPF dynamic routing protocol. Configuration volume is minimal. Okay, moving on. The working mode of dynamic routing protocols. We mainly divide into distance vector, classified into two types based on classification method, distance vector dynamic routing protocol and link state dynamic routing protocol. How does a distance vector dynamic routing protocol work? We take a diagram and use this diagram to calculate. Suppose we want to run a distance vector dynamic routing protocol among these three routers. So, the distance vector dynamic routing protocol. Its characteristic is very simple and clear, called rumor spreading, heard through the grapevine. Rumor spreading, heard through the grapevine. What does rumor spreading mean? What does heard through the grapevine mean? First, we need to clarify one point. Every dynamic routing protocol has its own database. For instance, our distance vector dynamic routing protocol's representative are, for example, IGRP. We will discuss IGRP next, this distance vector dynamic routing protocol. First, it only needs our devices to want to run a dynamic routing protocol. We create a process for the dynamic routing protocol. It will have this dynamic routing protocols called database. Then, in the database, I'll write in Chinese, okay? I won't write in English. Then every router we run a dynamic routing protocol. We will have this dynamic routing protocol corresponding database. This is our distance vector routing protocol database. So, if we have three devices in between, we run a distance vector dynamic routing protocol. Assume R1 on this side also has this loopback 0 interface address, is for example October 1st 10, 024ths. This October 1st 10, 124th is such an IPv4 address. For R3, let's assume there's another, which is October 3rd 10, 324ths. Both devices have a loopback 0 interface, a virtual interface we use for testing, for forming neighbor relationships. Suppose on R1 we run a distance vector dynamic routing protocol, running a distance vector routing protocol. If our interface, students, please note, before we study our path vector routing protocol, before BGP, our understanding of dynamic routing protocols needs attention. We activating interfaces to allow our interfaces to run dynamic routing protocols. Suppose a distance vector routing protocol, our interface 0 runs a dynamic routing protocol, IGRP. Then we will add the interface's directly connected routes to the database. For example, R1, our 0 interface address, 172.16.12.1, we will add the interface's directly connected route 172.16.12.0/24, directly connected route direct connect, ECT. Direct connect, right? ECT, is it spelled like this? Spelled wrong, isn't it? No mistake, right? Direct connect, we will store it in our IGRP database. After storing, what do we do? Similarly, for example, our loopback 0 interface also runs a distance vector routing protocol. We will also add our directly connected routes, the October 1st 10, 124th interface's directly connected route stored in such a database. I remembered wrong. Directly, missed an ly, put, find a drop connected, then placed in our database. R2 also runs a distance vector routing protocol, adds its own directly connected routes, for example, the 0 interface is running, puts it in its own database, a directly connected route, our directly connected route, 172.16.12.0/24, and our 10.1, suppose R2 does not have, There's also 192.168.23.0/24, our directly connected route, R3. Similarly, if the interface runs a distance vector routing protocol, our 23.0 directly connected route, October 3rd 10. 024's directly connected route will be placed in the database. Then what do we do? The so-called rumor spreading is easy to understand, like a network deployed like this, like an assembly line work. An assembly line, so-called rumor spreading. How a distance vector protocol works, I have a 10.10. 1.0/24, R1 says, I have 1, I'm connected to the October 1st 10. 024's network segment. Then I share this message, tell our other friends, like telling him, tell my neighbor, the neighbor tells my other neighbor, like the neighbor I received, my good brother R1 tells me he has a October 1st 10. 024's route, he's connected to the October 1st 10. 024's network segment. I know now, if I want to access the October 1st 10, 024's network segment, who do I go to? I go to him, he tells me he's connected to this network segment, right? What do I do if I want to access this website? I just go back to him, and it's all sorted, right? Just like in our rural villages, in our village, the next house had a big, chubby baby boy. The next house had a son, the neighbor tells me. I get the news from my neighbor. They say a son was born. Then, I know, later when I see a little chubby boy next door, I already know that he's the neighbor's son. Similarly, I pass the message to my neighbor. The message is told to the neighbor. The neighbor tells the neighbor's neighbor, today our next door had a son. Tomorrow the whole village knows. Why? You tell me, I tell him. The message is very well communicated. The whole village knows. You tell the message to my neighbor tells my neighbor's neighbor. Then I find out. The guy next door, R2, tells me he heard some news. Someone is connected to the 10.10.1.0 24 network segment. So later, R3, if I want to find 10.10, 1.0-24, I look for whom? The person who gave me the information. I go to R2. That's enough. That's how distance vector routers work. I pass the message. I share the routes I have. I tell you. You tell him. He tells another. So when accessing, what do? I just access it the other way around. Put it in this diagram. Why is it called rumor spreading and hearsay? Do you understand, students? Rumor spreading. You tell me, I tell him. Then R1 I tell R2. We exchange our database entries through dynamic routers. Of course, we will talk later about how. Dynamic routers, we can exchange our database entries. R1 tells R2 what? Then I'm connected to 10. 1.0-24, this network segment. I, R1, share my database entry with R2. This segment, I tell R2 my database entries. Then R2 knows. Who told me? R1 told me. So if later I want to access 10. 1.0, I go through R1, that's enough. Because he told me he has this network segment, R2 then tells who? Tells R3, then R3 I know, I find out from R2, he can access. R2 can access 10. 1.0-24, then we can calculate the database entry, turn it into a route, submit it to the routing table, then in R2's routing table there will be 10. 1.0-24, R1 told me, next hop is who? 172.16.12.1, he told me. He has the network segment. So when I want to access 10. 1.0, I just go back to him. We dynamic routers distance actually protocol. We can automatically exchange database entries and follow a principle. Whoever gives me the routing entry, my next hop points to whom. He tells me he has the network route. If later I want to access the network, I go to him. Turn it into a route entry submitted to the routing table. Our routers can normally forward according to the routes calculated by the dynamic routing protocol, and such a routing entry transmission. This is something that every router is doing. It's as if a very festive event has happened in R3. Throughout the village, every household experiences a joyous event. Then you pass it to me, I pass it to him, and we all exchange our fresh news with each other. R3 shares its routes, then tells R2, R3 informs R2, R2 then informs R1. We all pass on our respective R3 told me. Then R2 tells R1. R1 finds out 10.10.3.0. Whom do I go through? R2. We exchange our database entries with each other. Through these database entries, we can calculate into routing entries, submit to the routing table. Our routers can forward according to the routing table. This is the Distance Vector Dynamic Routing Protocol. Do you understand, students? Any doubts? Any confusion? Press 1. Any questions? No issues with the Distance Vector Dynamic Routing Protocol? Students, teacher, hello, I have a small question. Ask, can you hear me? Can hear you say it's about hearsay? Is it about the big chubby boy next door being born? Yes. Under what circumstances is it transmitted? Do I just need to plug in and I'll tell the other side? Or does it follow something? We will discuss this later, about how routing entries are announced, database entries, what methods they have. One way is periodic updates, meaning I tell him every so often, this is periodic updating. Another situation is called triggered updates, meaning if I just got such a message, I immediately tell him, but what you just mentioned about plugging in, that's not how it works. With IGRP, it's like this. When we just establish neighbors, you know me, I know you. When we just got to know each other, we exchange information. At that time, we exchange database entries. After exchanging, we both know each other well. From then on, only fresh things. New routes, we will announce. We will talk about this later. We will mention this later. Okay. Then, I'll wait to talk about it later. This is their method of announcing. We will discuss this place later. We will speak about this later. All right, then I'll wait for further discussion. This is his way of announcing. This is his method of announcing. So the use of distance vectors works like this. We announce our own database entries. We exchange with each other. Finally, each device among us has routes to our other sites. You tell me, I tell him. So this is one solution. Next, let's switch to another. So this is the working method of the Distance Vector Dynamic Routing Protocol, called rumor spreading style. It actually has many representatives, such as our RIP. It has two versions. RIP is the ancestor of our Distance Vector Dynamic Routing Protocol. It was the earliest to appear, around 1982. Sorry, 18 is too early, 1982. Distance Vector Routing Protocol. Two Americans, two chubby American guys, invented RIP. They thought static routing was too tiring, wondering if it could calculate itself. At that time, they invented something called Routing Information Protocol, called the Routing Information Protocol. And at that time, at the time of RIPv1, they discovered issues with class. Later, we found improvements, upgraded to RIPv2, including broadcasting update methods. Then it was upgraded. Both RIPv1 and RIPv2 are distance vector protocols. One is version 1, the other version 2. As for IGRP, it actually evolved from IGRP, known as the Internal Gateway Routing Protocol, the Internal Gateway Routing Protocol. However, this protocol actually shared the same flaws as RIPv1, similar drawbacks, so it was later upgraded. We upgraded to Enhanced Internal Gateway Routing Protocol, an enhanced version of the Internal Gateway Routing Protocol. And what else? There's also BGP, this protocol, but this protocol can't be considered a strict distance vector routing protocol. It's considered a path vector. So let's not discuss BGP here. So far, in the working context, the distance vector protocol, the public protocol, is either RIPv2, but RIPv2 is actually rarely used by manufacturers now. Very few manufacturers use the RIP protocol anymore, because it has many criticisms. When we are in NA, we will discuss what criticisms and problems RIPv2 has, what issues, so RIPv2 has already exited the market. Perhaps you will encounter it overseas, in more remote, older areas. You might encounter RIP protocol, but not so much in China anymore, almost not at all. So with the distance vector protocol, Cisco devices use EIGRP. If you're using Huawei or H3C devices, these public protocols, you probably won't use distance vector anymore. We all use link state now. Okay, students, this is how the distance vector routing protocol works, spreading rumors and hearsay, DUS.